So far in our Feff Fitting experience, we've worked really only with single scattering paths and shells that are pretty well isolated from one another. Now, fortunately, this isn't always the case, and some analyses take a little bit more work and or need multiple scattering paths in order to get a reasonable model for the structure. So in this video, we'll go over a case where multiple scattering is needed to understand any of the spectra at all. Hi, I'm Matt Newville, and this is part of the series using Larch for XAFS analysis. In this example, I have a spectra that I collected with a collaborator on a molecule. I'll see if I can pronounce it correctly. It's tricarbonyl cyclopentadienyl manganese. So it's a structure that looks like this. If I bring this in, there's a manganese atom shown here in purple, and then 3 carbon-oxygen carbonyl groups pointing off in different directions. And on the opposite side of the manganese is a pentagon of also of carbon. So there's carbon at this distance and 3 carbons and carbon-oxygen scatterings at those distances. So that's a fairly complicated structure compared to most of the things we've looked at so far, but it's not that unusual to believe that that could happen in any other organic molecules. And one of the things you'll notice is that because of this carbonyl, we have these straight lines of bonds from the manganese to the carbon with the oxygen in nearly a perfectly straight line with the carbon, so that the photoelectrons can scatter from the carbon or from the oxygen or go through both in multiple scatter in the forward direction. And that is highly favored and gives a strong amplitude. And that will interfere with getting a good XAFS spectra for this data set, and probably for any structure with carbonyl in it. So I'll leave that aside, and we'll go in and read the data that I have for this compound. This is in the same folder here. So there's manganese cyclopentadienyl carbonate data, and we bring it in. Now I should say, actually, this is also like when reading in data, the X array for this data set, which is fairly old, is a little bit hard to parse. I want to make sure that this data type is labeled as XAS data, not raw data. XAFS GUI, although it's all the data we've shown so far is actually XAFS data, it could import other ASCII data column files and be able to make simple plots of other kinds of data. But unless it's XAFS data, it won't be able to treat the data as extended XAFS, for example. So I want to make sure that I read it in as XAS data. And when I do that, we see that there's a nice pre-edge peak that we could analyze, as we talked about in many earlier videos, although that data is not very well sampled for pre-edge peaks, and that the data measured in fluorescence swoops up a little bit, as is typical for fluorescence data. This data is actually rather old. If we look at the XAFS, the extended XAFS data, we get something like this. So the data extends out to about K of 12 or so, which is, we talked about in earlier videos, is common for scattering of oxygen and carbon as well, because the scattering amplitude for those light elements just stops being very strong above about 10 inverse angstroms. So even if we had collected better data, unless it was a very low temperature, we probably wouldn't see much past 12 or 13 inverse angstroms anyway. So this data is real data. It has some noise in it, and that might be part of the story for the analysis. But we'll work with it anyway. If I plot the Fourier transform that we'll do with this, something like that is probably okay. So we're going out to a K of I'll just make these nice round numbers and sort of round down because there's noise in the data. K of 12, a Kaiser-Bessel window with a parameter of 4 to make that a nice broad window. Okay, so to do Feff fitting, now this data set also, like, just to be clear, this sort of organic compound is not listed in our CIF structure from the American Mineralogist collection. We need a separate CIF file. So in fact, I found a CIF file from the opencrystallography.net, the COD database of very many CIFs. I did have to edit it a little bit, and I'll explain what I did in a second. I edited it outside of this program. I actually added in the full reference. That's not necessarily that's not necessary, although I think it might be necessary for the version that's distributed at this time in Larch 0.953. That'll be fixed so that that's not necessary, and that parsing CIF files will get a little better. But what I really did that's important is I removed the hydrogen atoms from the CIF file. There's in the structure here, the white atoms are hydrogen. But those are and Feff8 can deal with hydrogen reasonably well. Feff6 cannot at all, or hardly at all. And also adding them into the structure makes the structure much harder to work with and deal with. And there's no scattering. There's essentially no scattering from hydrogen atoms, so it doesn't add an important contribution at all. So here, I should also say, like, just to be clear, I want to be clear. I don't want to do the carbon edge. I want to do the manganese edge. There are many carbon sites. I think this lists 8 separate carbon sites because for the structure, all of the carbon atoms are at slightly different positions. There is one manganese site because there's only one manganese in the molecule. I want to do the manganese site, so let me just read this Feff file a little bit. It's, you know, a bit of a mess, but it's K edge, and the absorbing atom I pot with 0 is manganese, and then there are carbon atoms. There are 3 carbon atoms at about 1.78 angstroms, say. Those must be the 3 carbons for the carbonyl. And then there's 5 that are around 2.12 angstroms. Those are the 5 for the pentyl ring, for the ring. And then there's 3 oxygens here that are, you can almost read that, are right beyond the carbon atoms. Those are the 3 oxygens. If I can pick the 3 oxygens, those are the 3 oxygens that are the oxygen part of the carbonyl. So there are all of those atoms, and then there's more stuff out here. So I'm just going to run Feff on that. I'm only going to go out to 5 angstroms on that while that's going to run. I did something wrong. Let's see what I did wrong. I have manganese and carbon out to 5 angstroms. Maybe I should go a little further out. Okay. There, it helped to go further out. I'm not sure why, but that's how you deal with when Feff doesn't work. You try it again when Feff doesn't conform to your needs. So there's a lot of paths here that it's enumerating. So it's going on. I'm going to try to go over to this data set in the XAFS and see if it's not responding, so I can't plot the chi-var data. We're just going to wait for that to finish running. There we go. Now, it did calculate a lot of paths, but I also want to look at this data in R space, which we haven't done yet. If I plot that in R space, we have what appears to be 2 different shells here. That's a little, I find this to be a little scary when I look at that, because if I zoom all the way out, as we talked about for doing background subtraction, I have an RBKG, the default value is 1. That carbon, or that manganese carbon distance is 1.78 angstroms. That's a little bit closer to do that. So I might look at, what if I make RBKG 0.9 or 0.8? Does that change the result much? I can see that as I adjust these windows, I can maybe see them both at the same time. 0.8 gives a little bit of an ugly thing there in the chi-var. 0.9 looks okay, and I might be able to change the K weighting as well if I do that in K weighting during the background subtraction. That, oh, not a 5, maybe of 1. No, that's not good. Let's try. I like, when I was playing with this before, I sort of like this combination of 0.9, and then I feel a little bit more confident about fitting that first shell that we have this well understood. It's already looking kind of complicated, and if I plot that as the real part of chi-var, there's real oscillations there, and I'm a little afraid, I might be a little afraid just from looking at this, that modeling that well is going to be challenging. But okay, so I think that's okay. I think we have a good XAFS spectrum there, and we're going to fit that. We're going out to k of 12 in the Fourier transform with a dk of 4. Maybe we can make that a little shorter. Let's just try that, maybe. Plotting the magnitude of chi of r looks like that. That looks okay. To me, let's just try, see if that's going to work okay. Okay, so let's begin with, by bringing in, for this Feff calculation, we'll bring in our paths. So we're going to pick this manganese. It didn't have a mineral name, so it says missing in it. And we have carbons. We have 8 carbon neighbors, but 3 of them are the 1.78, so I'll import only one of those. We don't need to import them all. We could, but we don't need to. And then we'll just remember that there are really 3 of those. And then for the ring at 2.12, there are 5 of those. I'll pick one in the middle and just import that. So the question is, can we just use the carbons and these sort of first single scattering paths to model this data? So I'm just going to assert that we don't know what that the structure is right, so that for the short distance there are 3 of them, and for the longer distance there are going to be 5 of the carbons. And again, if I plot chi of k for this, it peaks up at very low k, 2.5 angstroms, and the phase drops almost as minus k. The typical story that I will show you as many times as I can. And for the parameters, we have an S0 squared. We'll vary that in E0, 2 delta R's and 2 sigma squareds for the first 2 paths. But there's a question of what the fit range should be. So I'm going to plot those paths by themselves. And you can see that they plot here and here. And that's interesting because it sort of looks like they're at relatively low K, or relatively low R compared to the data we actually have, which is kind of odd and sort of disturbing that maybe we did a background subtraction problem, but also that there's a split here, and that maybe we can say these are the carbons, and then to do the carbonyl, we have to stop there. So if we stopped at that dip at 2 angstroms, let's try that fit. Let's just see what we get with that. We're starting at 0.9. There's actually a fair amount of weight from those 2 paths at low R. But let's do a fit and see what we get. And we get a fit that is here. There's quite a bit of like extra junk down at the bottom here. And if we plot that as the real part of chi of k, the fits actually looks pretty reasonable, out starting at even between out to 2 and starting at about 0.9. That looks pretty reasonable. We got a decent fit, didn't we? But now let's go look at the parameters that we got for this. We get a chi-squared 900, a reduced chi-squared. Wait, we must not have, we did go from 11.5. We went to R-min of between 0.9 and 2, and we get a chi-square of around 900, or a reduced chi-square of 700, partly because we have 6 variables with 7 independent points. So we're really stressing what we can do with the data here. We're very close to the number of actual independent points. And the fit gave an S0 squared of 0.6, and as we saw from other analyses, say of the iron oxide, that's not terrible. It's just maybe that's not great. But E0 is 20 volts. And the delta R's that we got for these 2 paths are around 0.6 and 0.04 and 0.06 angstroms. That's a bit far further than we would really like to have. But that E0 of 20 EV is worrying. That's a big shift. Like, as to say that it shifted by 20 volts would be that it could have jumped a period. So in fact, if I plot the chi of k here, it looks actually not very convincing. Now we saw earlier that with the iron oxide or other spectra that the first shell fit doesn't really look like the data in chi of k. But if I go back here and take those values, so I can, from this I can say update model with these values. That fills in all of these points. And now if I plot the data with the current model, I get that. That's our fit. But what if I change that E0 back to a value closer, let's just make it 1. That's a reasonable value for E0. If I plot that with all of the parameters as fitted, but the E0 is 1. That's not a very good fit, especially when I look at that in the real part of chi of k without the paths, maybe. That's not very good. That's not a good fit. They're almost out of phase. And if I look at that in k-space, there's definitely something, well, something odd. That doesn't look quite right. It would be nice. You can also see that because we have two paths and they're at close distances but not identical, that they have this beating and then this place where they go to 0. So it would have been nice to have data that went out further. Of course, the oxygen or the carbon scattering doesn't go out that far very well. So you really need exquisite data and probably at low temperature to be able to see, go out to 15 or 16 angstroms and see the carbon scattering have a minimum there. We don't have that data. We have this data, but also something looks like it must not be quite right with this data set, with this set of parameters. And the issue is really that we didn't include the multiple scattering. So in our model, while putting this back, we included the manganese, the purple manganese, to the close carbon. That's the one at 1.78. And we included the ring carbons at 2.12. But these oxygen bonds are not that far away, and have strong amplitude because of the multiple scattering paths. If we look at, I'm just going to slide that over. If we look at the data again in chi of r, also just from what we saw with our fits to iron oxide, we're fitting this part, we're not doing very well, and we're completely ignoring this peak. We stopped at 2 angstroms as if saying that there is a clean break between the spectrum, and we know that that's really probably not the case. And if we look at, so let's bring in some of those multiple scattering paths. So we'll go find those and figure out what they are. So we need the manganese, carbon carbonate. Those are all at 2.8. Those are the paths that go from one carbon in the ring to another carbon in the ring. So that's the ring to ring carbons. And you can see that the amplitudes for those, the expected amplitudes for those are pretty low. They're 18 compared to out of 100 is a maximum of 100. Not quite a maximum of 100, because if we continue down, we see that there's a manganese oxygen at 2.93 angstroms. We're going to want that. That's the further oxygen. And then there's one more at 2.932. So there's 2 in one of those. So there's 3 of those oxygens. But then we have these manganese oxygen carbon and manganese carbon oxygen carbon manganese scattering paths that have amplitudes that are higher even than the first path. So those are important to include. We have so we'll want to include the manganese oxygen, and we'll want to include the manganese oxygen carbon, and we'll want to include the manganese carbon oxygen carbon, the 4-legged path, the triple scattering path. We'll want to include those. Now, I'll say that we'll bring those in, and we'll just assert that there's 3 of each of those. In fact, the manganese oxygen carbon, and then there's other multiple scattering paths that go to within the ring, going from a carbon to another carbon that's not a near neighbor but across the ring. That's what all of those are, and those all have much lower scattering probability. We'll just neglect those, at least for now. We'll neglect those in total. I won't keep you that long. So we'll include these 3 scattering paths. Now, we already know that we're close to our limit of information. So I'm just going to assert, I'm going to close this now. I'm just going to assert that, so now we have carbon at 178, carbon at 212, oxygen at 293, oxygen carbon at 293, and carbon oxygen carbon at 293. Those are all the same, and we have 3. This is the carbon of the carbonyl. This is the oxygen of the carbonyl. I'm just going to assert that there are 3 of those, and I'm going to assert that there are 3 of those. Actually, I should probably assert that there are 6 of those, because it can go from the oxygen to the carbon and back, or it can go from the carbon and the oxygen back, and they're pretty much the same. So I'll assert that there are 6 of those, and then the carbon, oxygen, carbon, there are 3 of those. And we do have different paths. We do have different delta R's and sigma squares for all of these paths. And let's just go do something simple to reduce the number of variables, because we go to the parameters page, we now have what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 variables. And we'll want to be able to fit out probably out to what, 3 angstroms. So if we go to, say we go to 3 angstroms, but that's still not going to be very sufficient. But if I plot the current model as it is, plot the current model with all of those paths, you can see that now we have something that's, well, not actually very close to right, but we're getting there for modeling this data here. That might partly be because we have these terrible values that we included from earlier. So I'm just going to assert that those delta R's are around 0.01 or 0.001. I'll call this one 0.01. What the heck? And we have sigma squareds that should be not too small. But also I can say that for all of these distances that are at 2.93, all of these, let's just say they all have the same delta R. Now the bond could bend or extend or so on. I think that for now we're just going to ignore that possibility and just say that if the oxygen moves from 2.93 to 2.94, say, that the oxygen-carbon bond should also move the same distance. So let's just say that that's, without the caps lock on, delta R 293. That's going to be the same parameter to make that distance vary. And I'm going to do the same thing with the multiple scattering path. That's also going to be del R 293. So I'm going to do the same thing for the sigma squareds. So I'm not actually adding any parameters here. I'm going to say that's also sigma squared. Now you could argue that maybe the sigma squared should be different, or even a multiplicative factor. So maybe it should be times 1.5 or something. I'm not going to worry about that yet. I'm just going to leave that as it is. That is, you may say that the disorder for a multiple scattering path has to include the fact that the middle atom might move so that the distribution of distances that you see is slightly bigger. It won't be smaller, I'm almost certain, but it might be bigger. But for now, I'm just going to assert that they're all the same, so that we still actually have 1, 2, 3, 4, 5, 6, 7, 8 variables. And I'm asserting that our structure, that this is the right structure, that it's 5 in the ring and 3 for the carbonyls. We can test that next, but let's just try that. If I plot that current model, it's still not great, but let's do a fit to that, and we get a much better result. Now that's the fit, and that I'm calling that like not too bad. If we plot the real, we've actually done a good job on all of the phase of the real part of chi of R, and in chi of K we've done a pretty good job of modeling that data now, by including those multiple scattering paths. Even though we didn't really refine them much, we did get a decent result. Let's see, the fit is still not great. Its reduced chi-square is 200 compared to, it's better than 600, but it could be better than that, I think. It would be nice if it was better. It's still not perfect. There's a lot we've glossed over or forgot about, right? We let all those distances be constrained. But also, if we look at this, the parameters now are the sigma squareds are in the 10 to the minus 3 range with uncertainties that are 1 times 10 to the minus 3. S0 squared is 0.8. E0 is 8 volts. That's much better. I'm much less concerned that effectively the oscillations jumped a period or inverted if the E0 is is 10 volts or less. And now the distances have refined to very small values. So actually that's saying that the structure is very consistent with the starting crystal structure data. So if we look at the path parameters, we get that, I'm just going to go all the way down to the carbonyl distance, the carbon at 1.78, the distance is 1.78, 1.79. And the ring is 2.13. Pretty good. And the oxygens are also, those are forced to be also at a distance that's from the carbon bond. Is that right? Yeah. So then the 2.93 for all of the further away oxygens. The oxygen carbon, and the carbon oxygen carbon multiple scattering are all at a distance of 2.93, which is consistent. So that's saying that in this picture of the molecule, that the oxygen is 2.93 angstroms away, the carbon is 1.78, and then these carbons in the ring are 2.12 angstroms away. Okay, I'll just slide that off the screen. So we have a pretty good fit then with this data set. Now we can do the same thing that we did before, because fitting S0 squared gave a good fit, and we saw that S0 squared was refined to 0.8. That's a totally reasonable value. But we might want to say, let's vary the coordination number for those as well, forcing them to be the right number for each of the multiple scattering paths. So we know this is going to work, but I'm just going to, let's just do this. Let's just say, let's call this N, and I'll just give this a different name, N-carbonyl. That's for the carbonyl path. And this one's going to be N-ring. N-ring. Again, the parameter names are not constrained to be these with the little path label. It's just that those are convenient. So here, these should all be N-carbonyl. Of course, I chose to spell carbonyl. Maybe I can do a copy and paste. Copy, and then go here and do, actually that was 2 times that, right? Because we're accounting for carbon scattering from the manganese to the furthest oxygen to the carbon and back, or to the carbon and then to the oxygen. So path reversal symmetry. And in the list, that was how those were distributed. And I'll paste that. So that's carbonyl. And now we'll go to our parameters page, and the carbonyl should be 3, and the ring should be 5. And we're going to then set S0 squared to not 0.9. Now we know this is going to work, but that'll give us some idea of the relative uncertainties in the coordination numbers for those two paths. And actually, for this, it adds a variable. So it's a good question whether this is a better fit to vary the coordination numbers independently. So now we have 9 parameters out of 13 independent points. So we're doing okay. The reduced chi-square actually got a little worse. So it was a little worse to allow those two coordination numbers to vary independently, which is an indication that our asserting that there was one S0 squared and we knew what the distances was actually pretty good. So here, again, we set S0 squared, and the distances, delta R's, are very small, suggesting that the distances we started with in the structure were right, and that the ring, it says that there are 4 in the ring and 3 in 2.7 plus or minus 0.4 of the carbonyls. So that's good. That's pretty close to as well as you can expect to saying there are 3 and the ring is 4 or 5. That's completely reasonable. If you could just adjust S0 squared down a bit to bring those up. So let's just go try that. If I had just said that S0 squared was not 0.9 but 0.8, then we could redo the fit. We're going to get the same numerical results for n times S0 squared. So these are all the same, but the values for n now are 3.03 and 4.5. Plus or minus 1. So that's pretty good. If you wanted to argue that suggests that the number in the ring could be 4 as well as 5, then you're actually right. I think we're almost done with this example, showing that sometimes, including multiple scattering paths, are important even for understanding the first shell of a system. But if you knew that you were going in with a structure this complicated that had 2 different distances, including a relatively short carbonyl bond, then you might be aware of that if you have these kinds of bonds in your system, that you might need to take care of that. Let's look at then at the magnitude of chi of r and plot each path independently. There's a lot of paths here, so this is kind of a mess, but let's go look at that again, because I'll take out the data. Take out the data because the data is interesting, but not the main thing. I'm going to get rid of these longer bonds because still we have this story that those are carbon of our carbonyl, and the carbon of the ring, those are the magnitudes, and they add up to give that portion of the red spectra. The ring structures are actually pretty weak in there. They're not zero, but they're pretty weak in that range. But they still contribute. And when we do not the magnitude, but the real part of chi of r, it's possibly a bloody mess in there that we have almost no hope of disentangling those different paths. And that's why we had to include them all, because at 2 angstroms, if we look at what's going on there at 2 angstroms, it's challenging to tell anything for those different contributions from those different paths adding up just are all over the place. That's one distance, that's another distance. Then we got this thing and this thing. They're not huge, but in this range, they're all over. And the fact that the magnitude of chi of r has this dip at 2 angstroms is completely accidental. That's just the way the phases for those happen to add up. There's not a lack of atoms or a lack of contributions there. They just add sort of destructively. It doesn't go to 0, you'll notice. It just goes down. They add sort of destructively there, and that's a good indication that the paths are not separate if it doesn't go to 0. So interpreting that simple dip as meaning that's where there are separations of paths is probably wrong and going to lead to the kind of crazy results and E0 values of 20 volts that we saw for the first fit that we did with this data set. So I hope that scares you a little bit into thinking about doing XAFS on complicated molecules. Then again, this worked. So once we got it right, once we included the fact that it had carbonyls and what that meant for modeling the data, once we included that, even with kind of noisy data from actually a long time ago, it worked out. So I hope that scares you a little bit for doing any analysis on truly unknown systems, especially truly unknown systems that have organic bonds in them, but that also it gives you some confidence of how you can approach dealing with those kinds of systems, those kinds of spectra, and that and give you some confidence that this XAFS analysis can be done even on rather complicated systems. So if you have any comments or questions about this system or this example, please leave them in the comment section below, and I hope you find this helpful. Thanks.